Okay, guys, so this time we're going to continue with the discussion of Riemann integrals and talk a little bit about the properties that they have and maybe do some examples with that and see how far we can go with it. If you remember last class, we said that you're dealing with, at this point I said a function f of x that's positive, a continuous on an open or a closed interval a b. So that was what the restriction we've had so far. And this is your f of x. And I told you guys that what we're trying to calculate is the area under the curve. It makes sense because it was a positive function. What I'm going to do is I'm going to remove the positivity requirement at this point. I'm going to say, suppose that my function actually dips down under the x-axis a little bit. Does it change anything? Well, it really doesn't change anything because if you partition, and then again, partitioning could be happening the same process as you did before. And you can have certain number of partition, regular partitioning. And then you can do left endpoint or right endpoint approximation like you did in the last one. So you can do left endpoint, for example. And then for this one, you can do left endpoint. And then for this one, you can do left endpoint, left endpoint, left endpoint, and then left endpoint. And then calculate these. And again, this is just for one partition, obviously. But one thing to notice is for these, you are above x-axis, right? Which means your f of x is actually positive, whatever x, let's just say xi stars are. But for these, you're below x-axis. Which means your f of xi stars would actually be negative. So when you multiply those by delta x, you get a positive quantity on the top, and you get a negative quantity at the bottom. So that's how you're going to end up having to factor that in your calculations. So in a way, what you will end up with is what we call a net area, where above counts as positive, below counts as negative, and you're calculating the difference of those positive plus the negative. Now for a function that, again, just for example, if I give you a function that looks like this, a straight line that, let's suppose it's y equal to x negative x plus 2. And if that straight line goes from, say, over the interval 0 to 4, you're going to have a little area above the x-axis and an area, the same equal area below the x-axis. The area of the top is 1/2 2 times 2 because it's a right triangle. The area below the x-axis would be 1/2 again, 2 times 2. They both are the same. This would be negative because it's below. That would be positive. So the net area would be 2 minus 2, which is 0. So if somebody says, what is integral from 0 to 4 of negative x plus 2 dx, you would say that's 0. Net area. If there is more above x-axis than there is below x-axis, it would be positive. If there's more below x-axis than is above x-axis, it would be negative. And you can have any combination of that. Multiple pieces, some on top, some on the bottom, and so forth. So when we talk about net area, that's what we're talking about. In a homework, you guys probably looked at situations where, or you will look at situations where it asks you to do something using geometry. It says use geometry to calculate the integral. And what they're saying is something like what I did here, is your shapes, you're still interpreting the integral as the area bounded by the curve and the x-axis, positive above x-axis, and if it's below x-axis, it will be negative. And you just calculate the areas of the pieces, the parts, and then you try to combine it and see what happens there. So that's very important to know that now we no longer require our function to be positive functions. Later on, we're going to remove the continuity requirement as well. And then, of course, the being over the closed interval, when we talk about improper integrals, we're going to talk about removing that as well. So we're going to have a more general theory for Riemann integrals. Just a reminder, again, Riemann integral, when I talk about Riemann integral from a to b of f of x dx, is just a quick reminder. It's really limit as n goes to infinity of sum I equal to 1 to n f of xi star delta x, where delta x is b minus a over n, if the limit exists. Just a quick reminder. Okay. Now, the next thing that I would like to talk about is some properties of integrals, properties of this notation I have introduced to you guys. Some of these properties are very simple, very easy to see and accept. Some require a little bit more justification for, which hopefully we can provide you with that. So properties of integral. One of the, I guess the most obvious one is, again, going along the geometry idea, if that the integral of any constant function over an interval is nothing other than the multiplying the constant times the length of the integral. And this is not a groundbreaking idea. You probably would think about it yourself. If you think about it, if you have a constant value c for an integral over an a to b, then the area under the curve, which is what the integral represents, would be the area of that rectangle, which is b minus a as your length, times the width, the height in this case, which is going to be c, so c times b minus a. So that's one property of integral. You'll see that again, you'll use that in your calculations. Second one is, how does the integrals operate when you're adding a function to another function? So if I have integral a to b of f of x, and then I'm adding to that g of x. If I have two functions and their addition, I'm taking the integral of that. It is actually, it does behave the way you want it to behave. It's actually going to be a to b of f of x dx plus integral a to b of g of x dx. So it does in fact behave as you would want it to. Now, of course, I can justify this. Visually, of course, you can do this, but if you want, or you also can justify it using the summation. You could say integral from a to b of f of x. And again, this is beyond what you're expected to do, but you can rewrite it as a Riemann sum, Riemann as n goes to infinity, of sum I equal to 1 to n of f of xi star, again, assuming that partitioning has happened, plus g of xi star times delta x being b minus a over n. You can distribute that. And then you can split the sum into two summations, assuming the sums, of course, are finite sums in this case. As I say, it's a very tedious process if writing every step. And then I can split the limit, assuming both limits exist. I can split it into two. And obviously, the first one is the definition of the Riemann integral of the f of x. And the second one is a definition of the Riemann integral for g of x. So that probably can easily be verified. Again, you could do that for many of these, but at some point I'm going to stop doing it just because it's not necessary and it could distract you from what the main point is. The next one, the next property is integral from a to b of a constant multiple of a function, is actually the constant can be pulled out. No surprise there. You can do the same thing. You can do it with the summation, write out the summation, the constant comes out of the summation. The constant also comes out of the limit part, so you just get the integral times the constant. And then, of course, the same thing for the plus can be said about the minus. So actually, let me just save myself some time. If it's a minus, you will get a minus. All of those will be minuses. So the property is actually, if you sub difference of it, you actually get difference of the sums, the integrals. So I'll just skip the math property. Your book states it as a separate property altogether. Two other properties that are very important, but they only require really just one integral sign is one. Now, what happens if you just go from a point to the same point, assuming the function is continuous at that point? What would the value of the function be? What would the value of integral be? If you're just over the same point and the function is continuous, what's the area about that point? Of course, it would be 0. The two-dimensional area is 0. The next requires a little bit of understanding of what that dx delta x actually represents. What happens if I go from a to b f of x, now change my direction and go b to a f of x dx? Which means instead of saying b minus a over n, I'm doing a minus b over n. A is a smaller number than b. So delta x will be a minus b over n, which is negative b minus a over n. So it has a negative value to it. So this actually will be negative of. So switching the bounds of integration actually changes the sign of the integral. It goes from positive to negative, negative to positive. It doesn't always just make it negative. It goes from positive to negative, negative to positive, depending on what the sign is. Okay. So those are some of the properties of integral. Another property that actually is very useful, we use them, in fact, we're going to use it when we prove fundamental theorem of calculus. But right now, it may feel like, why is the necessity of that? But another property that's very, very important is if I have an integral that goes from a to c, for example, of a function, and to that, I add integral from c to b of the same function. What I end up with is really going directly from a to b of f of x dx. Now, the big picture that helps you understand that, again, we're assuming that the function is continuous. We are still requiring the things that I said at the beginning. So we are dealing with a continuous function, and then we're assuming that the bounds are you're over a closed interval in all these cases. Pictures that really helps you see this a little bit better is if C falls in between A and B. So if I have A, C, B, and this is my function, then obviously you can see that this area is represented with this integral. This area is represented with this integral. And a total area is represented with this integral. And obviously, visually, you can see and accept that. But one thing that you have to have in mind is there's no necessity for C to be between A and B. I could actually, it's kind of counterintuitive, but I could actually think about A, B, and C, as long as, again, your function is continuous over those. Now, integral from A to C, the blue part would be all of this. Integral from C to B would be actually negative of this. So it's like I have the blue, then I take away the green because this quantity would be now negative. And of course, it would now, the remaining would be the orange part. So C need not be between A and B, but visually speaking, it's more pleasant if C is in between A and B. yet another property of integration. Okay. Now, some of the other properties involve comparison, comparing functions with functions, and the positive and negative values of the function. So, which property? No, property 7 is actually if I have a positive function, and for x values between let's say a and b, so the function doesn't have to be positive everywhere, but if it's positive in that interval, then I can be sure, and again we're assuming continuity of the function, I can be sure that the integral from a to b of f of x is positive or 0. Now, if I have a function that is greater than or equal to another function, again, for x values between a and b, again, we're only looking at one portion, not the whole thing, then I can say that then the integral of the smaller function over that interval is less than or equal to the integral of the bigger function on that interval. Or in this case, f is bigger, so. Which in a way, in an interesting way, leads to a method of approximating integral, a very rough approximation of integrals. By the way, the numbering of the properties does not match the numbering of the properties in the book because I reordered things slightly and also add some things in between. So you may notice that there's the mismatch of the reordering, the properties there. If I have a function f that falls between a number m and a number capital M, so capital M represents a bigger number and lowercase represents a smaller number, for all x between a and b, then putting a lot of these properties together, I could say that the integral from a to b of f of x dx is between m b minus a and m b minus a. Now, I actually can have a very nice little picture for you guys to represent what's going on here. So if I have a function, and let me actually make sure that it is it has correct, yeah, so you don't feel like it has to be. This is a, this is b. The least value of the function is m. The highest value of the function is capital A. Then what this approximation says, it says that the area below the curve is between the area below the m and the area below n. So the actual, maybe I'll do it with this, the actual area below the curve falls between the area below the lowercase m and the below the capital M. It's not different than saying integral from a to b of m dx is less than or equal to integral from a to b of f dx and integral from a to b of m dx. So it kind of goes along the way of the second comparison property. And then each of these integrals really are same as when we have a constant, which we said, if you have a constant, it's just constant times length of the interval. So that's what that is. Now it's kind of like, I tell students, it's like, well, okay, think about it. If you're going to get gas and you're like, well, I'm not sure if I have enough money for gas. And you're like, well, I know the price of gas is probably around between $3 and $4. So, you know, the price of gas is definitely more than $3 and definitely less than $4. And then you're like, well, and I know I have a 15-gallon tank. Then you say, okay, the least I need to have for this is the least price if I want to fill up my tank would be $3 times 15 gallon, $45. Or at most, I would need 4 times $15, which $4 times 15 gallon, which would be $60. So I need between $45 to $60. It's a very rough estimate. But you're like, well, if you're just trying to estimate it, you're like, well, that's just how it is. It's like the least price for the gas is $3. The maximum price is $4. And I have 15-gallon tank. So the price of filling up the tank would be between $45 to $60. That's kind of like this. I like this example I usually give. I say approximate this. And you're like, okay, so my f of x is root x, and between 1 and 4, 1 is here, 4 is here. The minimum value is 1, the maximum value is 2. So that integral would be between 1 times 4 minus 1 and 2 times 4 minus 1, which is between 3 and 6. Very rough estimation, very rough estimation. You have a better luck by just using partitioning. Even 2-4 partitions will do a better job than this. But still, it is something that can be used. And this also is something I'm going to use in the next section. My next lecture is when I'm actually proving the fundamental theorem calculus. Okay. All right. So I hope this will help you with answering homework questions from section 5.2. One of the things that shows up in homework a lot, you see a connection between integration and distance velocity relation. So just to justify that for you guys, let me explain. If I have a velocity curve for a motion of an object, so it tells you how fast the object is moving at any given time. And I want to know what's the total distance traveled by the object. It's not hard to see it if it was constant velocity. If an object was going, say, at 2 miles per hour, and it went for, say, 4 hours, then you say 2 miles per hour times 4 hours is on 8 miles. That's very, very straightforward. But if the velocity is some function of time, it changes as t changes. It's very hard to do this. But what we could do is we could partition it. And we could say, well, okay, suppose that these are units of time. So this is t1, this is t2, this is t3, this is t4, t5, and say t6 for the sake of argument here. Then I can say, suppose for the first t1 minutes or hours or whatever, the units you're using, I'm going to suppose that I go with the same velocity that I had starting point. And then for the second, I'm going to go with the same velocity. For the third, I'm going to keep the same velocity. In a way, I'm doing what I did earlier when I created the rectangles. And you can do that for all of them. The area of this would be the time times velocity, just like here, which gives you the distance. d1. This one will give you d2, this one will give you d3, and so forth. But obviously, these are approximations, not exact values, because you did not consider the change of velocity as time changed. You improve that approximation by increasing the number of partitions and increasing the number of partitions and taking the limit. So really and of course that process is calculating the integral. So the integral of a velocity is actually the distance traveled. You see that in homework a lot in the form of a table, in the form of graphs. They're trying to get you to decide what the distance is, the total distance is, by looking at the velocity. And of course, if the object actually, the velocity is negative, the object actually has negative velocity, that means it's going backward, then the net area is actually your displacement. Okay, so the integral of absolute value of v of t is the distance traveled. Integral of v of t is displacement. If I make everything positive, I didn't have to worry about that here because the function was positive. But when I introduce negative values for v, because v of course could be negative, then in that case, I'm going to have two cases. Do I want the displacement or do I want a total distance travel? Total distance travel is always the absolute value function, make it positive. And if you go forward, count it. If you go backward, make it positive so it doesn't cancel out any of the forward motion. So the absolute value, integral of the absolute value is the distance traveled. Integral of the function is a net distance, which is the displacement. So I hope this helps you answer some of the homework problems.